Hi everyone, my name is Shizhe. I'm postdoc researcher at NeurIPS. I present our work, History-Aware Multimodal Transformer for Vision and Language Navigation. This is a joint work with Pierre-Louis, Cordelia Schmid, and Ivan Laptev. Vision and Language Navigation, VLN for short, aims to train autonomous agents that can follow natural language instructions to navigate in realistic environments. The agents won't be given a fully observed map of the environment. Instead, it just can obtain a panoramic observation at each step. To accomplish this task, it should understand the language instruction, such as the meaning of turn left and continue up the stairs. And then it should associate the language with its observation. For example, which direction is left and where are the stairs in this panorama. It should sequentially make actions given the instruction and observations until it stops at the target location. The VLN agent is faced with several new challenges. First, the agent is in a dynamic environment and should continuously align the new observations with the instruction. Therefore, it is essential to keep track of the navigation state, which is helpful to comprehensively understand the environment and also improve instruction grounding. However, existing works mainly adopt a fixed-size recurrent unit to encode the whole history sequence, which might be suboptimal to capture essential information, especially in extended navigation trajectories. Another challenge concerns about learning good visual representations. The representation should be generalizable for semantic scene understanding, especially on unseen environments. It also should be good at inferring spatial relationship, because spatial relation is widely used in navigation instructions. For example, with a bed on your left, turn right to the bathroom. Existing works, however, many use CNN features pre-trained on auto-domain datasets and never optimize the feature. So the visual representations can also be suboptimal for the VLN task. To address the above challenges, we propose the History-Aware Multimodal Transformer, HAMT. I'll briefly introduce its framework. For each navigation step, our HAMT model is fed with text input, the instruction, history input, a sequence of panoramic images in previous steps, and current observation, the panoramic image of the current step. We use several unimodal transformers to encode each modality input. Then a cross-modal transformer takes all the modalities for cross-modal reasoning. Finally, an action prediction head is used to predict the next action. It is a fully transformer-based architecture for multimodal decision-making. The HAMT enables long-term history modeling. It learns the dependency of all panoramic observations and actions in the history sequence for action prediction. It also enables end-to-end optimization for visual representations. The fully transformer-based architecture allows efficient end-to-end training for VLN tasks. But there are several problems. First, it is computationally expensive to encode all panoramas in the history. Assume there are k views in each panorama and t steps. Then the computational cost of a vanilla transformer is k squared times t squared. Second, the action prediction task alone might be inefficient to learn generalizable models. For the first problem, we propose a hierarchical history encoder for efficient and effective history encoding. We first use visual transformer VIT to encode each view image in the panorama. Then, we propose a panoramic transformer to learn the spatial relationship within the panorama and obtain a global panorama embedding. Finally, we use a temporal transformer to encode temporal relationships across panoramas in the history. Such hierarchical encoding significantly improves the computational efficiency. For the second problem of learning better representations, we use several proxy tasks to train HAMT in an end-to-end manner. Apart from the common visual and language proxy tasks like mask language modeling, mask region modeling, and instruction trajectory matching, we further propose two new tasks for VLN. The first is single-step action prediction or regression. It aims to learn how to align the observation and the text given history to predict the next action. The second is spatial relationship prediction, which aims to predict the relative spatial relations of two views in the panorama. For example, in this panorama observation, it should predict the door is on the left of the chair. We fine-tune HAMT on each downstream VLN task via reinforcement learning and imitation learning. We design rewards for different VLN tasks. More details are presented in our paper. We evaluate HAMT on a diverse range of VLN tasks. The room-to-room and the room-across-room dataset are VLN tasks with fine-grained instructions, which requires continuous instruction grounding. The reverie and the room-to-room loss datasets are VLN with high-level instructions, which requires to better capture the scene memory. The CVDN belongs to vision and dialogue navigation. It emphasizes on dialogue history understanding. And the final room-for-room and the room-to-room back datasets are for long horizon VLN. The room-for-room concatenates two passes in room-to-room, and room-to-room back is our newly introduced setup. It asks the model to return back to the start after arriving at the original location. Therefore, the last two datasets more emphasizes on long-term scene memory understanding and instruction grounding. Our HAMT model outperforms state-of-the-art on all datasets. Especially, we obtain more than 12% on room-across-room, 5% on room-for-room, and about 7% on room-to-room back. We also carry out extensive ablations to understand our HAMT model. A key question to ask is, how important is the history encoding? We compare with a recurrent model with fixed vector to encode the whole history, and a temporal-only model which only selects one view per panorama to improve efficiency. The results demonstrate that our hierarchical history encoding is better for the VLN task. The second question is, how much does the visual representation help? We compare with resonant features pre-trained on ImageNet, the VIT features pre-trained on ImageNet, and our end-to-end optimized VIT features on the VLN dataset. The results shows that the VIT features outperforms the resonant feature, and the end-to-end optimization can further improve the performance. The last question is, how effective are the proposed proxy tasks for end-to-end training? We compare three models. The first only uses common vision and language proxy tasks. The second model further introduced the single action prediction task. And the last one combines the spatial relationship prediction task with all other tasks. The results show our proposed two new tasks are beneficial for the training. Here I will present a navigation example of a recurrent model and our HAMT model. The recurrent model correctly performs the first four actions in the instruction, such as work out, turn right, turn left, and work down. But it fails to track the last action in the instruction and turn to the wrong direction. Instead, our HAMT model is better at instruction grounding and state tracking, so it succeeds in this example. To conclude, in this work, we propose the first fully transformer-based model for the VLN task. It efficiently encodes long-horizon navigation history, and we propose several new proxy tasks to improve the end-to-end training. We fine-tune HAMT with reinforcement learning on the downstream VLN tasks and achieved state-of-the-art performance on a wide range of VLN datasets. Thank you for watching our video. Our code and pre-trained models are released in the following link.